Yeah, hi everybody. I'll probably do this in sections, several sections. For this is the review recording. Hopefully you can hear me. So what I do, so I'll probably just put this as review section one, review recording one, recording two, as I do them. I want to get started on this evening. It's a Sunday evening. You'll get it hopefully tomorrow morning. Nevertheless, what I do, since you're not familiar with me, is I look directly at the exam and try to give you an additional heads up on top of the study guide. So here it goes. Again, 65 questions. Certainly the chemistry part, that chapter 2 is the big focus point here, I would say, proportionally speaking. And this skips around because I had to make 3 different copies of the exam because we're so crowded. Well, the same exam, they just changed the batting order of the questions. They're all multiple choice, true, false, matching, that type of stuff. So here's the key. Literally, the answer key to the first one. I told you this was coming. I think every class. The key is, I'll read it to you. DNA only, RNA only, both DNA, neither DNA or RNA. You figure it out from there. I'll give you the names of the different components, the A's, the T's, the G's, the C's, anything else that's used, or for that matter, not used in the chemical sense. Your questions determine, is it just DNA or is it used only in RNA or is it used in both? So certainly if I said, trying to think of something that would be fairly obvious. If I said something like guanine, okay, which doesn't have to be one of the answers, that would be used basically in everything. So the answer would be both DNA and RNA, but that doesn't have to be one of the ones here, but it gives you an idea. Okay. I want you to know how DNA differs from RNA. The big things to remember, it's a double-stranded molecule. It's too big to leave the nucleus. We discussed that at considerable length several times during the course of the class. Okay. It gives its message to messenger RNA, and at that point, it's able to leave and do its stuff. So it's a double-stranded molecule. We know it has the A's, the T's, the G's, and the C's. We know about the hydrogen bonds being important. So those are the things that you have to be familiar with. So what's the big differences? And that's what you have to discern from this particular question. Okay. How does it differ? How does DNA differ from RNA? Okay. And then the different kinds of RNA. I went over those, transfer, ribosomal, messenger. I don't think at this point I'm asking you exactly what they do. I think you should be familiar with it to know that messenger RNA basically is the arm of what we call transcription. It's DNA's instructions to build proteins based on what we call the genetic code, and the genetic code is in the language of messenger RNA. So that's called transcription. Everything else, whether it's transfer or ribosomal RNA, is all about transcription. Transfer brings along the amino acids. Ribosomal RNA is part of the construction of the ribosome, which is where all this takes place. Looking at some of the chemistry, remember the idea of valence. Valence electrons are the electrons in the outermost orbital of any of these atoms that are unpaired. The valence number is the number that either they have to gain or to lose to either complete or empty the orbital. So if they have a +1 or +2, they'll lose 2. Okay, if they have 6 and they're like oxygen does, they're going to try to gain 2. So in that case, if they have to lose 2 or if they have to gain 2, the valence number is still 2. That's a significant feature. Mm-hmm. So you have to be on top of those things. And so understand those are things that want to, if you only had 1 electron, you want to lose it in a big way. If you had 7 of the 8, you want to gain 1 in a big way. And what does it become? What kind of charged particle? One thing I think I forgot to mention, well, I'm glad I'm having a chance to clarify it now, is one of the things that salts are. Salts are remarkably important in our body. Calcium, sodium, potassium, chloride. They are very chemically active. They are very physically stable. And I don't know why I forgot this in the classes, but there's so much trying to cover. Basically, salt's the kind of thing you could stick in an oven, do the experiment at home, crank up the oven high, put salt on a sheet pan, put down some parchment paper first or something underneath it, stick the salt in at 500, come back in an hour. Salt's still there. It's physically stable. It has a very, very high melting point and a very, very high freezing point. I mean, it's effectively something you can't achieve at home, but chemically, boy, you put it in water, it disappears. That's the idea of physical stability versus chemical stability. I went over certain normals, 37 degrees Celsius, pH 7.35 to 7.45. I give you a rough idea that the pulse should be between 60 and 100 normally. Blood pressure 120 over 80. Respirations could be 12 to 20. We call those things not the pH, but all those other things the vital signs. And a lot of what they reflect has to do, well, not so much reflect, but a lot of things that account for this are those wonderful properties of water. We give a name for them. We call them colligative properties of water. That's kind of the way water works with the hydrogen bonds. It's able to freeze in such a way that it stays intact some, but the bonds lengthen so it can float. So it basically absorbs energy in freezing. It absorbs energy in heating. Those are part of those properties. It has surface tension as well as being able to dissolve things and contributing a lot to pH. Really, the protons and the hydroxyl groups, the OH negatives, they come from the water more than anything else in a lot of ways. And getting to that, when we talk about acidity, it means it wants to donate a proton. You put it in water, it causes more protons to be available. A base or an alkaline substance you put in water causes less protons to be available. Okay, so if you have more release, doesn't matter what it is, the chemistry behind it. As long as it releases protons compared to what it was like before, it's an acid. If it absorbs them, and remember, protons are a hydrogen ion, then it's a base or an alkaline substance. The structure of amino acids is extraordinarily important. Okay, remember, you have what we call a central carbon, and then it has 4 bonding points. One is an acid, one is an amine group, so one's the name amino acids. One is just a hydrogen, and something else is called an R group. So the structure is the same. The variation is in the 20 different R groups, 8 to 9 of which, depending on the author. And I think when I phrase the question, it would be one of those numbers. I would not have 8 for one and 9 for another. That would be unfair. So you should be able to figure out the number of the 20, okay, that we can make. 8 to 9 of them are considered essential, must be acquired through diet. All the other ones can be made biologically by our own processes. We don't need those building blocks. We already have them. That's the idea of something essential. We have to acquire it through diet, like vitamins and minerals, certain kinds of fatty acids, one called arachidonic acid. That's all part of it. So the R groups are really important when we start to assemble polypeptides and proteins. Remember, the primary structure, the batting order, it plays a significant role in what's going to come afterwards. The role that it plays initially is just going to create the peptide bonds in the initial structure. The secondary structure is how it begins to shape itself based on hydrogen bonds. It will either form those spirals, those alpha helixes, or form those beta pleated sheets, which kind of come out looking a little bit like ribbon structure. That's the whole idea. You're either going to have that fan folding into sheets, or you're going to have spirals or helixes come to the party. The tertiary structure is all about the R groups. Are they positive or negative? They'll attract. Are they acid or basic? They'll seek to neutralize each other. Are they fat soluble or are they water soluble? Well, those are the big players. And then the quaternary structure is when we take polypeptides, or we take a protein that's already a protein. Remember, the difference is the number of amino acids. Adding them up, if you get 2 polypeptides at 80, magically have it, and they come together, now you have a protein of 160, 100 or more amino acids. That's sort of the standard definition that we have available to us. So I think that's really a good idea to know. So that's quaternary structure. And sometimes we'll have a metallic component like hemoglobin in it. We might have a mineral that acts to stabilize it or completes it. That's all part of it. So have an idea. So, okay. And so I have some of the questions are, which of the following of these answers is incorrect, or which of the following is correct? You have to read the question. So this one, if it's asking about DNA or RNA, if it says what's not correct, basically I go down the A, B, C, D, and E, or A, B, C, and D responses and put a check mark for true, or put the letter T or the letter F. And so I try to figure out which one is not correct. However you do it, but read the questions. The questions are intricate. And as you go along in your academic careers, they get more incorrect. So DNA, purines, 2 rings, right? Okay. Purines are part of it. Pyrimidines have 1 ring. Okay. Remember the A's and the T's and the G's and the C's. And the sugar is deoxyribose, and it forms an alpha double helix, or a spiral staircase, and it's held together by hydrogen bonds. That's the way it works. So as we move on, remember the things that are what we call the properties of life: being made out of cells, having both DNA and RNA, being able to replicate, or either be able to reproduce, either not necessarily sexually, but they must be able to reproduce in some way, shape, or form. Being able to respond to changes in the environment, that's responding to stimuli for you and I. Somebody touches you, you feel it, you can see it or hear something, whereas for lesser organisms, that's not the case. And so we're talking about the properties of life for everything. And being able to do what's called energy transformations. And energy transformations are just that: being able to take something and effectively garner the energy to survive from it. And doing so, you're undoubtedly going to create waste products as part of it. So those are all, that's the big thing when it comes to energy transformations. And again, cells being the main thing, that's the principle of cell theory. So I'm sure you've heard that many times before. The DNA and RNA are our definition. Everything has to be made out of cells, obviously. Being able to respond to stimuli, reproduce, because that's the only way it's going to, the species or the thing will flourish. And doing energy transformations, and effectively the respond, and have a boundary, which we know are membranes that are by definition semi-permeable. Understand the structure and remember of things like cholesterol. That's really important. It's got those 4 rings. It's bigger than that. Cholesterol has the side chains. We kind of lop those off to make estrogen and progesterone and testosterone, but the cholesterol itself is in there stabilizing membranes. The big deal: vitamins and minerals, which are essential. Vitamins are considered coenzymes, meaning they complete the enzyme most of the time. Cofactors are minerals. And again, they're useful to, maybe they create stability, they alter the shape, that kind of a thing. And most of the enzymes that we have been talking about, they're structural. Most of the enzymes that we are talking about are made out of proteins, and they act as what are called catalysts. So, I mean, that's the first little unit of questions. That's about a third of the exam. I'm going to stop there. It's kind of at night and my voice is going. Thank you. We'll continue with this. I'll get another section out to you, labeled section 2, maybe later this evening. Thanks, and bye-bye.